Hello, welcome to the second seminar of the AAAC of this year, and it's my pleasure to welcome Mohamed Chetouani for this session. I'm gonna read his bio, but I guess he doesn't need a presentation, but just a little bio that we put here on the website. He's currently full professor in signal processing and machine learning with human-machine interaction, deputy director of the Institute of Intelligent Systems and Robotics at Sorbonne University in Paris, that used to be known as Pierre-Marie Curie University. And his activities cover social signal processing, social robotics, interactive machine learning, with applications in psychiatry, psychology, social neuroscience, and education. He's also heavily involved in European projects. So he was a coordinator of the Marie Curie network animators training network, and it's also president. He was president of the ethics committee of the university, his university, until last year. And heavily involved also in educational activities, including summer schools, etc. And other projects include human-centered AI, or the EU projects, a network, and robotics. He has been general chair of ACM-ICNI, a very well-known conference, until last year. He is in charge of the inclusion of students with disabilities for the Faculty of Science and Engineering of Sorbonne University. And his free time, he has free time to give talks from time to time, like today. So thanks again for accepting. If I had to describe his work with just a sentence,
and that's the most interesting part. Yes, go.
I think I would choose social signal processing. I think that's kind of the sentence that comes to my mind when I think of you, apart from a very nice person, etc. But yeah. Okay. So the floor is yours. If you want to share your.
Okay. Thank you for the introduction. I should see the screen. And do the same. Thank you, Lola. Thank you also for the attendance. For the people, I recognize several names here that I know, and so thank you for being there. So I choose to when I was when Lola invited me, I was thinking about what I could talk, what could I say. So I was so I decided to talk about things that I'm quite interested now. So I probably have more questions than things, but we have been working on that. Is you see, I think the key word here is observers. Is how we can use observers, usually humans, but you will see not only to do two things: something that is natural behavior analysis, as we do in affective computing, basically, but something else also is how to generate. So you see that is also in some way quite old idea of doing analysis and synthesis. I'm not saying, and I will not show you things that are doing both analysis and synthesis. So it will be works on analysis and works on synthesis for several reasons, but we can discuss that later. So just, I like to start with the fact that there are already a lot of observers, so humans in the loop of most of our stuff. Here I took examples of machine learning process that we could basically have in affective computing, social signal processing, or human-robot interaction. So what you have on the left is really having a need of data, as we always have as an issue. So you may have users to provide the data, but you have also domain experts that are already here to say which kind of data we need, how to define a scenario, which kind of what is relevant or not. So this could be I call it domain expert, but this could be also a user. And then you have samples, you have databases, you have even preferences on the data. And you have a machine learning expert that usually does something like analyzing the data, so a bit of data science, designing the algorithms, evaluating them, and then you get models. Then sometimes, and this is a question that I will not discuss that today, but this is a big question, why they are different and should be different people, but here I put them explicitly different. You have human-machine interaction expert that design the interaction itself, how we interact, which kind of usability evaluation we could have, and then you have users. So you see there are already a lot of humans that are observing in some way. So what I call here, and then we will have definitions, a better definition of observer, is that we have humans that are observing, acting probably also on the data. So it's not necessarily observing, but by observing, they make decisions like annotation is a decision. Observing during algorithm evaluations and models is also a kind of observation and action. If you take this notion of observer, now, if you think about traditional, let's say, approaches that you could have in human-machine interaction, and we have that a lot also in human-robot interaction, is what we call BDI and things like that, where you try to build models of the other. And most when you want to build, let's say, models or robots that are aware of humans, you may have this kind of things, like you need to build a model of the human that is observing you and so on. So you can have different levels, but it is somewhere here, this notion of observer. So I'm not, so what this picture is saying is that I'm not doing as a robot the task for myself, but I'm doing that because someone is observing me or having some knowledge about me and trying to build a model of the other, who is also building a model of you. So that's the idea. So this is quite, I mean, interesting. And the point of the talk today is more to see what is the impact of this modeling, basically how we build this observer and what are the probably the impacts in two kind of situations. One is affective computing, so more trying to build machine learning models where we don't have actions, and the second one is more human-robot interaction where we have basically actions. So we have been doing that for recently also in this paper, is to think on and I will not go in all the details of this table because it might be complex, but I will focus probably on what we call inferential social agents, and I think that that's really important. So we have properties, and these properties are what we usually try to have in a human-centered robot learning. So it means situation when you have humans teaching robots, and you see there are things that you may know, probably not so, but open-ended learning, few-shot learning. So this is really something that most of the machine learning techniques try to address. You have this notion of being sensitive to social signals, which is not the case of all the machine learning techniques. But there is also this notion that now it's very important to have in some way, is having a better model of the learner, but also the teacher. And basically, so basically it's what we want to have is this kind of inferential social learning, or social agents. So inferential social agents means that we have agents, social agents, but they infer. So what we will discuss today is what we infer about the other, and they can infer several things. So you can imagine like modeling the learner itself, trying to model the let's say the strategy of teaching, the transparency. So when we say observer and the model of the other, we may have different directions. Some of them we can try to put all of them in the same model, but some of them are not relevant. So I will show only some of these dimensions today. So let's start by trying to get these observers, and I put computational observers just to understand what we mean by that. So I will start by something that we are working on is what we call communication and action, because it gives the idea of why an observer is interesting. So this is a work on by Marco and others colleagues on let's say basically cognitive science, but they use a lot of computational models. So here you have two parts of the figure. You have the planning and acting, and you have the inference. So planning and acting is when I plan. So these models are here to explain what humans are doing. But you will see later we can do something to generate actions. So planning and acting is when I have let's say I have an environment. So you see the model that has Bayesian networks. So you have an environment, and you have a goal. So we call it instrumental goal. So for example, instrumental goal could be I move this object from one place to another place. This is instrumental goal, so I have a task. So to generate a demonstration of it, I just need to know. So generating the plan. So it's basically I have a goal, I have the word, I generate a plan, so I generate a demonstration. Then on the right, you have the inference. So inference is when you observe. So you can have, and this is, I see in the attendance some people from speech processing and others. So it's a language is what we call literal observer. So you see, you observe a demonstration. So the idea is that from the observing a demonstration, you infer the goal. Okay, so it's what we call literal observer. So you see something, you infer directly the goal. So if you saw me moving this object, you understand that my goal is to move this object to one place to another. So this is the, let's say, the literal part of the step. But here, no one is taking the observer, the other, into account, and it comes to the literature that people try to take into account the other, and there are other different strategies. Here I'm just showing the strategy of this work because I like it, but there are others. So here, by taking into account, you see if they still have the instrumental goal, they still have the word, but you have the belief directed goal. So this means that we have a belief about what means this goal. Is it so there might be ambiguities on the goal, and we have an observer of a model. So when I generate a demonstration, and I'm not generating the demonstration for myself because just the goal and the environment, I generate the demonstration because I know what you and I have a model of you. For example, in teaching, this is very useful, and we will see that later when you do a pedagogical teaching or something like that. You need to take into account the others, obviously, because if you don't know their level, you just generate exercises, lectures, and others, but you don't know what they know. So this is very bad, and this is not the right way of doing that. And now so this is about the generation, and on the right where we have the inference, this is exactly the same thing, is that you observe a demonstration and you have models of the observer. This will help you to infer much better the goals. And that's the idea of the observer, is that now we have observers both in generation and both in the inference. That's the idea. I mean, this is also quite natural to do that. I mean, we always do that. I don't know if you know this kind of works, but there are two works that are interesting that we have been working a lot on mother-based infant-directed speech, and the difference between adult-directed speech and infant-directed speech. What you could see here is basically the kind of fundamental frequency changing, and we exaggerate. But why we exaggerate? Because we have the observer model in some way. Because we think that we direct the speech to someone. So this is communicative. We are not doing just the instrumental goal, just saying something, but we say something to someone. So this is also known in pet-directed speech, for example. On the left, you have similar things that have been done by some colleagues, and you have the reference here. They call it the acoustic packaging, and like this idea is that when you move objects here, you have someone who is moving an object and showing the object. And what is interesting, you have a kind of multimodal motion and moveries because you want to highlight something to the observer. Okay, and that's quite natural, and we do that in natural way. And I didn't show that in this today because we don't have time, but there are a lot of evidence done in neuroscience and developmental psychology showing that infants are very sensitive to that. If you do that, it's also to attract attention to because you could say why we exaggerate language. For example, in prosody, it's not useful. It's not the way people will learn language, but it's very useful in the way to attract attention, for example. Okay, so now let's go to the affective computing. So probably you know this kind of ways of doing annotation. Probably so here I'm taking an example of stress, and you will understand why we do that on stress. But it's a work that we did some years ago. So let's say you have someone who is stressed. So I will not talk today probably about details of the experiment, but if you want, because that's not the focus, we can discuss that. I will just show some results on that. I just wanted to discuss about this notion of observer. So what we do in affective computing is that you have someone, and you see SA is kind of self-assessment. So you have an experiment. So here it was about stress. So you could have internal, let's say, mental states, and you produce, when you do that, you produce body movements, speech, facial expression, and others. But you have also what we could call internal cues. And if, for example, heart rate is about that, skin or silk conductivity is about cues that you have. So in this work, what we wanted to do is a multiple assessment, and then you will understand the clinical application just after. But we investigated this idea of observer. So you have the human, so the participant could provide for each video, for example, his own state. Okay, so which is called self-assessment. But you could have observers that are observing also the video, as we do in affective computing usually, and doing annotation. What is interesting is that we have this kind of external observer. Now we can usually we have few, but we can have crowdsourcing, for example, and you could have, let's say, a lot of external observers. So here we have to be careful because for one data or one video, what is happening is that you have only one self-assessment, of course, but you may have a lot of external assessment, and they might disagree, of course. What we did also in this work is to have a psychiatrist, but he's also a physiologist, to not have a look to the videos, but having a look only to the physiological signals, because it was stress, and trying to detect, to infer stress from that. And that's another view of the same phenomena in some way, because the affect is there. Is it stressful or not? That's a question. The level is a question. But we are already able to do this kind of stuff, is having videos, physiological signals, and having a look in different ways to the same phenomena. So you can understand that now what is the ground truth, because after is you want to train models, because you have videos and you want to train models, and usually you use either the self-assessment, the external assessment, or you do something, but you need to put something on your machine learning models. I will show you how we did that. But for that, I will explain you why we came to that. So there were theoretical reasons, or let's say empirical reasons to affective computing. But what I'm doing in my group is having also, let's say, practical and pragmatic applications of that. And clinics is also interesting for us. And here we were working with adolescents that have kind of let's say issues regarding the way psychiatric issues, like the way they feel their own emotions. Okay, so that's interesting. Is that the way they are observed and the way they really feel the emotions is different, basically. And this is what we call borderline adolescence. And there is a high risk of suicide and others, and there are a lot of troubles. So what we wanted to know is, are we able to evaluate or to quantify a bit more this idea of being a separation between the self-perception and the external perception, which is an very old question in psychology in some way. But here it was a clinical application. So we used exactly the context that you had before, is collecting self-assessment and external observers, both in physiological and behavioral cues, and to train models. For the physiological, we had other data that was hormonal. So not only, and this is also for Lola, we collected hormones at this time, and not only neurovagal information, and we were able to annotate both from the self-perception and the heteroperception. So here what you get is the rating. Basically, just on the ratings, when you see the control group and the borderline, you could see the level that's different. Of course, there is a difference between the self and the hetero. So self is when you annotate yourself, and the hetero perception where other people are doing the annotation. So it's normal to have difference between self and hetero. But we were really interested by the question of what is the level, what is the dynamics of that, what is happening when you do this kind of stuff. If you go for borderline, if you do, if you are control group, you could already see that if we have to design a automatic stress detection system, just by the rating, we may have different results just by that. So from the starting point of the decision of who is the observer, we have different results. So here you have it's what we did basically. Since we have the data, we use behavioral features, maybe not explaining the features, but there is basic things in machine learning and computer vision and signal processing. But here the idea was to use the tools to do borderline and control and self and hetero perception. And you could see that of course it's working, so we can train models, but we never get the same the same results and this is kind of the message is that just by deciding the way we annotate the videos and the data, in particular in emotions and affective states, we will have different results. We will have necessarily different results. Yeah, I'm not saying this is bad or good, but in few cases, we know how the data have been annotated. And in most of the cases is external observers, because it's very difficult to have also the self-assessment. In particular, when we have been looking to the multimodal, you see the multimodal, for example, for the self and the hetero. So when we take all the data, I mean, it's not only physiological, not only behavior, not only physiological, but we take everything. We don't have too much difference between on the control group. But for the borderline, it's different. It's really different, and that was something that we are still trying to investigate. We have also reverse problems, like you could see for the control. It's the performance has less for the hetero than the self. Probably meaning that it's easier, but for the borderline, it's the reverse. So we just by doing that, we have also ways of quantifying the difference between hetero, and we put some metrics between hetero and personality and self-perception. So now going to HRI. This notion of observer, where we have it in several ways. Of course, we have the same thing as, but I didn't want to talk about it. Is like when you observe robots, let's say motion or emotions of robots, and you do annotation. Of course, you will not have self-assessment of the robot, but you have external assessment. I'm not talking about that. I'm more talking now about when we generate motion. that we take into account the observer. And one use case that is very relevant in robotics is what we call legible motion generation. And the idea of legible motion generation is basically by the motion itself, you communicate the intention. And you have this nice picture of that is explaining that you have a goal, so a red or red or green, and you have a trajectory. And if it is a goal to action, which could be like what we said about literal, I ask you to go to the goal, you go directly to the goal. And here in red and green this is the inference that you have, because when you start, you don't know. So you don't know if you go on the red as an observer. Here still you don't know, but when you reach the goal, you know. So the idea of legible motion generation is, instead of doing something like I just minimize the cost, so just going directly, I do more than that. I take into account. So when I generate when the robot will generate the action, it will take into account the human. So the inference. So here you see is what is the priority of a goal given a trajectory. So the idea is that the trajectory itself should tell you which goal. So it's what we have here, kind of exaggeration. It's not useful for the robot at all. Okay, for the robot, there is no reason to do that. But for the observer, it's useful. Okay, because you are observing my action, how we do that. So there are a lot of mathematical models for doing that. Here I'm just showing the basic stuff, but there have been a lot of works on that. So for example, here it's the cost, and basically it says, okay, if you want to predict the goal, you just minimize the cost. So what is the cost? Might be the distance, the effort you will have to do for an object. That's the idea. And this is what we use in robotics, minimizing the cost. But the legibility score is a kind of trying to infer. So you get, again, the goal given a part of the trajectory, not all the trajectory, because if you get all the trajectory, you know you reach the goal. So there is no reason to communicate now. And you have a penalty term that is the timing. Okay. Of course, when you start, it's more difficult to infer, but if you are at the end of the trajectory, it's easier. So that's the end. So we are, and all the job of the method is to build kind of estimation of this probability and generate the right trajectory for doing exactly the same thing. Okay. So there have been a lot of works doing that, and Anfedrakan is an example. There are other examples. So that Rashid Isfer has been working a lot also on this notion of legibility, how we do that on motion planning or even task planner. But what I wanted to, and all of them needs to have this kind of being aware of the observer. So what we have been doing, so this is an example where we try to say, okay, it's cool to have the observer, but we don't know what to put in this model. What could we do for that? Because this will depend on the humans. Humans are different. It depends on the task. So what we did is a very simple task as before. So you have objects here. You have a Frank-Chemical robot, so very simple robot, and you want to generate trajectories that are legible for an observer. So we did that in real robots, but we also did that let's say in virtual or in simulation. And why we did that in simulation is that we use that to generate a lot of trajectories. So we have been using machine learning and to sample, because that's not so easy, but I will not go on details, but we have to sample the environment in a way that you can generate for one object a trajectory that might be legible. And then we ask humans, basically. We did exactly what we do in affective computing. We ask humans about a score of legibility. Okay, that was the idea. And people were here to rank the trajectory, to say this one is much better than this one. We tested several things. And what we did here is that by using, so exactly what we do in affective computing. So you have a trajectory, a motion, and an evaluation of it. So we learned a model. basically. We were learning a model. So here you have the trajectories. You see several trajectories plus, so each time you have a goal, you have a trajectory. And so you have a goal position. And then what the idea was, could we, for each trajectory, for each goal at control points, compute a score. So the score is obtained by annotation, and then the system. So we learn this model, and the idea is that now our model is able to do kind of a value function. So for people in reinforcement learning, it looks very similar to the value function. It takes states, actions, and then is able to give you a value of that, and we integrate that on time. So it's similar to what the probability system was approach was doing, but here we use annotations, basically same thing, annotations and so it's what we call computational observer models. So it's this idea of being able through the annotations to infer, to build like a human. And now what is interesting is that you can use this model to generalize to other trajectories and to ask the model, I give you a new trajectory. Before doing it, is it which kind of value of legibility score? So how a human will infer the legibility and the goal of the trajectory. So we use that in several ways, and we use different let's say. We compare that to different metrics because in the literature there are different metrics for doing legibility. Dragon is what I show you before is really the score where you have the probability and you penalize by other stuff. You have let's say on the other side you have Nicolaitis, which is more about the position, also the point of view, because it could change if I'm in front or not in front of the system. It could change. And we slots V is our model, and T-Rex is a basic inverse reinforcement learning technique that is taking the trajectories and trying to do the same thing. And you could see that for most of the cases, for different data sets and also different problems, because we change the trajectory, the goal position, the number of goals. So these are different tests. We are able to be very efficient in terms of doing that. So this notion of annotations could also help for doing let's say building observers that we can use for this. So of course there are limitations because you need to do annotation, but and also but there are similar problems, and I see similar limitation that what we have been doing so far in affective computing. But that's interesting because we can generate by doing that legible motions. Now I move to teaching because that's something that I like, and you will see that observer is important. So why observer is important? When I started, I said that teaching is also about observation of the learner. So there is this notion of what we call pedagogical reasoning or pedagogical learning, as you want. When you teach, you have this problem, basically. As a teacher, you have an hypothesis. You want to teach something. So what you do, you generate data. Okay? It's what we do. We generate lectures, things like that, or examples. And the learner is observing only the data and trying to infer the hypothesis. Okay. And most of the things in pedagogical reasoning is to have a loop on that and work on that. And something that has been done a lot is trying to use Bayesian models for doing that. So you have an hypothesis, you have data, so you generate the data given an hypothesis, and of course the Bayesian models are able to do that by trying to reverse the problem, and then if you have the given data, you try to infer the hypothesis. But what is interesting with humans is that we play with that. We are able to change a bit the probabilities by doing that. We adapt to the others. And on the right, you have an example of that. Here, this is a very simple maze. So you have a starting point, a goal, okay? And you have what we call safe colors, okay? So safe means that you can go there, no problem. So it means that the other is unsafe, you cannot go there. So in this work, the colleagues were asking people, do the maze, doing. That's why we call it doing. So just do it. And this is exactly what we show with predictability is you minimize the cost. So you ask me to do it, I do it. Okay. Now they were saying, okay, show your partner that the safe colors are. So you see the difference. The difference is really important is that here you try to take into account the observer. By doing, you do it. By showing, this is already communicative. You try to do the things, but not for yourself, for the others. Okay. And here they do things that are not relevant for the task, but relevant for the communication. But since you have only one way of communicating, as I show you for the legibility, you need to change the trajectory, okay, by doing that. And that's the idea, is that the people who are doing this demonstration are expecting that you understand that I want to show you two things, that how to reach the goal, and this is unsafe, okay? That's the idea. So we have been trying to say, okay, could we build models that are doing that exactly? So here it's a bit complex architecture, but you will see since we have been discussing about little and pedagogical, this is quite similar. So what you have on the top is basically what we do in learning from demonstration. So you have a pre-trained models. Okay, so you have a list of goals. So here it's moving objects to a cube, but it could be another task. We have been working on several tasks, but it's you have goals, you have a demonstration. So the teacher will select inside the goals, inside the goals and the demonstration, which demonstration I can give you. So if the goal is blue close to green, it's simple. I take the blue, I do it. So it's naive. And in traditional learning from demonstration, you have little approaches because you see a trajectory, you try to replicate the trajectory. That's what we do in imitation learning, for example. But that's not really relevant because now we don't take into account. It's really naive and little. So if we want to do more, it's not possible with the models. So what we did is what you have on the bottom. We built a pedagogical learner. So the pedagogical teacher. So the pedagogical teacher is doing two things. This is a reinforcement learning mechanism. So it has two goals. One goal for doing the task, one reward for doing the task, but also one reward to see how it will be inferred by the other. I explain you. So here you see a Bayesian goal inference. So what the system is doing is when you try to find a solution for a goal, okay, like moving an object to another place, you have to replay the trajectory and put that in a Bayesian goal inference and try to infer what is the goal. Okay. For example, I managed to do that for the goal. Then I try to infer what the learner will infer from that. Okay. And this is done by Bayesian goal inference. And how we do that, if you want, we can discuss that mathematically, but basically how we do that is that you have, this is a policy that you are learning, okay? And we replay with the policy, okay? We use the demonstration that we just learned. It's not only one, it's of course a batch. And we fix the policy, so not changing the policy. You use the policy to infer the goal. Okay, that's basically that. And we did a similar mechanism now for the learner. So the pragmatic learner has two things. So the literal is just inferring the Bayesian goal and doing the goal. This is the literal. But the Bayesian, the pragmatic has another reward that is infer the goal demonstration, but also train to infer own goals to better interpret demonstration. So what does it mean? It has exactly the same mechanism. Once the learner learns something, it uses his own policy, his own demonstrations, say his own trajectories to replay itself and say, okay, I can infer the goal. I know the goal, so I play it and infer myself to the goal. And I get another reward for that. So the difference between the literal and the pragmatic is that the literal is just inferring and trying to do the goal, to master the goal, while the pragmatic is inferring the goal, but also learning to better infer the goal. That's the idea. It has another reward to be better in the inference of the order. So back to the observer, you see that the teacher, the pedagogical, it has not really an observer model. Not technically, it's not like we said, I have a model of the other, but what I have is a model by an internal model that is still an observer. It doesn't necessarily fit the learner, but it learns an observer, still a model. And the pragmatic model is doing exactly the same thing. What is, of course, missing is a loop here, but we will discuss that just after. So if you try to infer that, to do that in robotics, so this has been done in work on robotics. So you have different metrics. One is goal inference accuracy. Is the learner able to correctly infer goals given demonstration from a teacher? Okay, so this is basically the observer. I observe a demonstration. I just want to know what is the goal, what is the goal. I have on goal inference accuracy. Is the agent, ever the teacher or the learner, able to correctly infer goals from its own trajectories? So you play yourself and you see if you are able to, so if the things that you are producing make sense. Okay, in other words. And the last thing, which is the goal, the second thing is the goal reaching accuracy, which is basically what we want in the end of the day, is that your robot should be able to reach goals. Okay, so it's what we want. And after we just put a metric that is basically the ability to of course infer, because since inference may have an impact on reaching, we just put a metric that is basically the same. So first thing is that why we use that, why we are doing that. First thing is that and in which situation we have that. We may have this problem in a situation where we have very few demonstrations. For example, here in yellow, you have the learner trained without demonstration. So the system is just trying to learn. So of course it could learn, okay? It could learn a task. So the task was again taking objects and making different figures, pyramids and others. They might be, or putting the blue in front of the red. They might be, you can imagine different, let's say, goals on that. And the system is able to learn. But now, if you use a demonstration, it says that demonstration is helpful in reinforcement learning to learn much faster. But you would say it's what we could expect, is that because here we have the help of the teacher. But what is interesting is what is the role of the mechanism? What is important? Is it to observe the teacher or the learner observing being pragmatic or being literal is useful. So here we played with the number of the demonstrations, and you have the goal inference and the goal reaching. I will not probably go on the other metrics. So inference is I'm able to infer the goal. So of course, in naive and literal, you are not very good at learning when you inferring the goal, because there is no way of explicitly learning that. But if I increase the number of demonstration, of course you increase your inference, because we use the policy to infer. Okay. But what is very interesting is that when you start now to combine pragmatic, naive, or pedagogical literal, you see that pedagogical pragmatic, so when you have inference, is very robust. Okay, it's very robust in terms of performance. So of course it changes a bit on the inference, but in terms of let's say of reaching the goals, is very good. I mean, it's really robust. So this means that with few demonstration, because you are not only copying or mimicking the trajectory, but you infer the goal and then you try to do the goal. That's it. Okay. Um, yes. So So the last part that I wanted to show you is how we use that in probably more advanced models. And one way is to think about what we call Lola, could you hear me?
On t'entend, hein. Enfin,
Okay, because I
Yes,
think
sorry,
Lola.
I was muted. You couldn't hear
Okay,
my-
because I was
Yes,
not
yes.
sure if someone was there. Okay, great. Okay, thank you. So I just wanted to the last part, when we is about, because what I didn't use the term theory of mind so far, but I think most of you recognize this kind of stuff. So what I wanted to show you is how we use that for and this notion of observation. So just okay. So it's a work that we have been doing, Clémence and Hugo and Olivier last year during the training period of Clémence. I showed that because it's related to this notion of observation. And what we did here is inspired by some works on influential social learning in neuroscience. So the idea is that if we observe a learner, then we will be able to build the model of the learner and then use this model to better teach. And this is basically what we have been doing. So here what we do is we observe a learner in very basic, very simple, let's say, environment, and we try to build a theory of mind of a model. And then the idea is, again, it was a learning from demonstration environment. Then the idea is to use the demonstration, this star model that we built to better predict what we call the reward, but also the utility to select the demonstrations, to select the demonstration. But you understand that the environment is different. And the idea is that for a different environment, now that we know much better the learner we have observed, we'll be able to teach and to do the demonstration by demonstration. So it is called, it's really this kind of idea of sampling the demonstration, because we have a set of demonstration and we need to select them. It's what we have in machine teaching, in terms of machine teaching. I will not go in all the details, but what is interesting probably here, I just wanted to be back on that, on this notion of utility, because maybe it's not something that all of us know. Is more about, you have a reward. So so you have the learner, you have a demonstration, and the utility is basically the reward minus the cost of the demonstration. And this is something that we have usually in machine teaching, is that we cannot provide a lot of demonstration because each demonstration has a cost. And in robotics, we know that. In human also interaction, human-human interaction, we have this issue, is that you cannot provide thousands of demonstrations. So utility is really this idea of the reward. The problem is that, so basically, if I know the reward and I know the cost, is somewhat easy, is that you just try to maximize this function, and you get the best demonstration or set of demonstration that you could use for your learner. The problem is that you don't know. I mean, you don't really have access to that. So you try to, by observation, to build models of that. And so you have only an estimation of that. So it's why you have an estimation of the reward plus a belief and a belief here. And all the work that we did is having models of that, trying to have models of that. We take into account cost or not. The details are in the paper, but here you get basically the ideas, is that we build different teachers. One is the aligned teacher, Tom teacher. It has it has the knowledge of the learner's policy. Okay, you have access to exactly the learner, or you have access to the learner policy, and you try to infer this policy. The rational term teacher is that the expectation is that the assumption is that the learner is rational, and for that we use Boltzmann policy. And by Boltzmann you have of course parameters of the Boltzmann, but you have to infer that. But that's interesting because you just minimize. I mean, there is less assumption. The assumption is not you have access to all the policy, but you have an assumption of the kind of policy you have. Then we compare that to several, let's say, baselines. One is the omniscient teacher, which is quite traditional in machine teaching, is that you know the goal, you know the observation function, you know basically everything from the learner. So it's a kind of upper bound teacher utilities. Then you have the reward optimal, non-adaptive. So here means that we select the demonstration by maximizing the reward, but we don't take into account the cost, for example. So we just optimize the cost, the So we have the utility optimal but non-adaptive. So we select the demonstration, but what we do is we don't know. We are not adaptive to the teacher. I mean, we can observe several learners. So I built a general model of the learner. While in the top teacher, what is interesting is that we are specific to the learner. So if I observe, let's say, five learners, in the top teachers, I will, in the end of the day, have 5 models. I've been able to teach the 5 learners because they have different, let's say, policies, skills, and others. While in the utility optimal non-adaptive, I just make a mean of it. Okay, so it's something very global. Like when you teach let's say in school, you have a class and you take just the mean of it. It doesn't really work. And the uniform is just you sample uniformly a learner. You don't so you don't really know what are the performance of your learner. You just make it uniform. So here to make it in terms of performance, so the performance is still the utility. So utility is really again the reward minus the cost. So we want to maximize it. So the receptive fit is that because you recognize that in the experiment that I show you is a mini grid. So the agents in the mini grid in the environment they have a receptive fit. So means what they can see, what they cannot see. So these are kind of perceptive skills that they have. So in robotics means that you have different skills, and here it's a skill about perception, but we can imagine different skills like manipulation others. So if I observe everything, so here you have the different, let's say, so you have in black the upper bound, and you have the 2 ones that are the let's say the new models. If you have full observation, you see that it's, I think the take-home message here is that, of course, if you have omniscient, you are very good in terms of utility. But what is interesting is that if I'm aligned or rational, I'm very good also. Of course, it's what we expect. But we can see, for example, that the reward is not really working here. It's not very efficient in terms of models. Now, if you go on the other side, when you have a receptive field that is free, so it means that if this is a very limited learner, you see the robustness. The idea is to have kind of a robustness of the model, and we can see here that if even if we have different learners, with different receptive fields, what is interesting is that the system is quite robust. Being able, so the best would be to have access to everything. But if we don't have access to everything, we can just have access to the policy. And policy is probably already a strong assumption. But if we just make rational, have the assumption of rationality, we are already very robust in terms of let's say of estimation of the utility, and we are very useful. So for the learner. Okay, so if we try to summarize and to let's have time also to discuss, because the idea is, as I told you, is more to have discussions also with you. If we start with the last part, is that this idea of computational observers, I think we are at today I didn't discuss about other models, but we are trying, for example, to investigate other approaches like in foundational models and others. But that's in the same philosophy of building computational observers that are able to be, let's say, to have human-aware systems. And for the generation of behaviors, that's really interesting because we can also, and what will be relevant with these models is that you can play with the level of awareness you want to have. So if I want to communicate a lot, of course, maybe I will be less efficient, but sometimes I want to be really efficient. I don't really care about the observer. So these are things that we probably need also to investigate more about how to integrate that in online, let's say, techniques that you build the models. And the main problem today is that we rely on very long observation, either with annotation or observation with the last work that I showed you. But what will be interesting is to have kind of what we do is online adaptation and observation and action that we try to do, even if we probably use pre-trained models or assumption. And in affective computing, things are quite similar. You saw that there is a question about the performance of the system, but let's say this is something that is already addressed, but there are few databases where we have this idea of several assessment. And I think it's also a way probably to work on the, let's say, validity or reliability or probably or even reproducibility of our work is to work with different let's say, annotations and try to optimize also agreement between these different views, and not only between the different annotators, but also different views. And that's important to take into account, and probably this could be a good step to improve our databases. And in my case, we have, let's say, a lot of clinical applications of that, but there might be others. Here we are discussing today about schizophrenia, and we use that also in autism. There are a lot of questions that are related to the way you express or you feel your own emotions in different situations. It's true also for aging, for example. So there might be several situations where we may want to have this idea of observers during the data collection. Okay, so that's all for my side. And question.
Thank you very much, Mohamed.
Let's stop sharing.
Welcome to the call, everyone. And I'm gonna stop the recording so that people can ask questions. But actually, you know, when I introduced you, I said, oh, what comes to my mind is social signal processing. So maybe next time I have to introduce you to give a talk, I'll think of education. Anyway, thank you very much. I'll stop here.